Hi, welcome back once again to AP Physics with Mr. O'Hagan. Today we're going to be talking about kinetic energy of rotation. There it is, right there. So let's start off with, so we're going to have an object rotating. We're going to see the kinetic energy of it. Duh. All right, but let's start off with talking about translation. So if I've got an object that's just translating, so here's my object, and it's translating to the right. If we assume that it's just one object of some mass m, the kinetic energy equals 1/2 mass times its speed squared. So let's say it's moving to the right with some type of speed, okay? All right, now, if I want the kinetic energy of a system of particles, so here we go. So let's divide this thing up into 4 different things. All right, each one has 1/4 m. All right, I know that's really small. So what happens is our kinetic energy ends up being equal to 1/2 1/4 m v squared plus 1/2 times 1/4 m times v squared plus, maybe I should put my plus down here, plus 1/2 1/4 m v squared plus 1/2 times 1/4 m v squared. And the thing I want to make clear here is that the v's are the exact same for every one of these objects because it's translating. So when I add this all up, so thinking about a system of particles, kinetic energy of a system of particles translating, we end up with the kinetic energy ends up being 1/2, and I've got 4 of these quarter m's, so that just makes it m, and then v squared. And of course, we're right back to where we started from. So if an object's translating, we can think of it as just one particle, or we can think of it as several particles, add up all the kinetic energies, and we're back to where we start from. Okay, so that's how you work rotational energy, kinetic energy of an object translating. And we've done that forever, no big deal. So now, so this is for the translation, translation. So now let's talk about rotation, rotation. And we're going to get a little bit of a problem here. And here's our problem. So let's say here's our object. And again, it has a mass of m. All right. So each one of these is 1/4 m, 1/4 m, 1/4 m, 1/4 m. All right. Now, let's say, just because I want to, just to draw the point, let's say that we're going to rotate this thing about, I don't know, this point right here. This is our rotation. Wow, I can't read that. That's our rotation point. If we do that, what you see is each one of these will have a different velocity. So it's almost like there's going to be a circular path. So this one's velocity will be kind of up in this way and fairly fast. This one's velocity will be down and fairly fast. This one will be up this direction and not as fast because it's much closer to the rotational center. This one will be down and to the right and kind of slow because it's much closer to the rotational center. All right, objects further away from the rotational center end up going faster. That's why I always pick the outside horse on a merry-go-round, all right, or a carousel. All right, you just go further. All right, anyway, so now if you do this, here's what happens. You got kinetic energy equals 1/2 times 1/4 m times v1 squared. And I'll make this, I'll give each one of them a number. I'll make this one 1, this one 2, this one 3, and this one 4. And I know you can't read those numbers, but I don't care. All right, but anyway, you get the idea. Plus 1/2 times 1/4 m times v2 squared plus 1/2 times 1/4 m times V3 squared plus 1/2 times 1/4 m times V4 squared. And here's the deal. V1 is not equal to V2, is not equal to V3, is not equal to V4. Actually, in our case, V1 and 2 would be equal as far as speed goes, and 3 and 4 would be equal as far as speed goes. But the idea is that there's not anything that's common. So you can't just do what we did up here and say all the V's are the same, add up all the masses, and get back to the kinetic energy being equal to 1/2 mass times some common V squared. Okay, that just doesn't work for rotation. So that's the problem we've set up. So here's how we fix this. Here's how we actually get to kinetic energy of rotation. All right, so let's go back to any object. Okay, so any object. Let's make it some crazy blah blah. All right, there's the object, and let's say here is the pivot point. Okay, that everything's going to rotate about, and it's going to go about this way, and we're going to divide this up into a bazillion itty-bitty particles. All right. Okay, so there's a little mesh on this of itty-bitty particles, and we're going to find the rotational energy. The kinetic energy of each one independently. Then we're going to add them all together. So here's what we get. We get, and this should not be anything surprising, we get the kinetic energy equals, all right, 1/2 mass of my first particle in here, velocity of that first particle squared, plus 1/2 mass of my second particle, velocity of my second particle squared, plus 1/2 mass of my third particle, velocity of my third particle squared, plus, for as many particles you have in there, you know, it could be 1,000, could be 100, whatever, because you're going to divide this thing up. Okay, yeah, nobody likes writing this way, so let's write it this way. Kinetic energy equals the summation of 1/2 mass I, velocity I squared, and there's ways to write this like n equals 1 to I or something. I can't remember. But anyway, I'm just going to add them all up. So let's not get all crazy about this. Okay. All right. All the velocities for all those different objects, are not the same. So let's write that down. Velocities, velocities, are not same. I actually really what I should say is speeds. Because in kinetic energy, we're talking about speeds. So the speeds are not the same. Okay, that's a problem. But you know what is the same? The angular velocity or the angular speed is the same. Because if you think about this, so let's put like some little like lines here. All right. Every point on every one of these lines, and I don't care what radial line you put here, is sweeping out the same number of radians each second. All right, because every single part of this goes all the way around in the same amount of time. I don't care if you're a part far away or a part close. It takes same amount of time to go all the way around. Same amount of time. That's the period. All right, so the velocity is for one rotation. The angular velocity, angular velocity is 2 pi over the period. Well, guess what? They're all going, once around, they're all going 2 pi for the angle, and they're all taking the exact same amount of time to get around there. So they all have the same angular velocity or angular speed. So here we go. Angular speeds, A-N-G-U-L-A-R, speeds are the same. Yay! Woo! Whoo! All right, that's going to be good for us. So we can rewrite this because I know how to go between regular speeds and angular speeds. So I'm going to make a substitution here for the angular speed. So let me think if I can do this right. All right, so here's how I do this. because I'm not good at this. So remember, I go back to SOAR. So this is the linear part. That's the angular part. So V equals omega R. Okay, so here we go. Let's now make our substitution into this. So the kinetic energy ends up being the summation of 1/2 mass I times, all right, here we go. I'm going to put another parenthesis in here, omega radius I, and that's squared. Okay, big parentheses around the whole thing. All right, and I don't need a subscript around my omega because they all have the same speeds. Remember? All right, so I don't need that little I there. Okay, so now I'm going to rearrange this ever so slightly. Okay, and here's my rearrangement. Kinetic energy equals 1/2 the summation of mass I, radius I squared times angular velocity squared. This is looking very much like our kinetic energy equation. The only thing is that this chunk right here, this part right here, this is something called rotational inertia. And rotational inertia is a capital I. So I can rewrite this equation as the kinetic energy of rotation, I'll even put a little subscript there so we know exactly what we're talking about, equals 1/2 I omega squared. All right, where I equals the summation of mass I, radius I squared. All right, so this is called rotational inertia. Here's our kinetic energy of rotation. Here's our rotational inertia. This rotational inertia is the rotational equivalent to mass. All right, an object that is rotating wants to keep on rotating. Hey, Newton's first law, okay, unless an unbalanced force, unbalanced torque, we'll get to torques later, act upon it, okay? The amount of resistance to changes in its angular velocity has to do with, not its mass, it has to do with the mass and where the mass is distributed. If I take, okay, let's use a pen, all right? If I take my pen, and this is not a really good example because it's so small. But anyway, think about this with a big giant bar, or a baseball bat. So I take a baseball bat and I hold it like this. It's really easy to, and I'm just going to support it. It's really easy to spin it this way. It doesn't take any effort at all to change its angular velocity. Okay? Very little torque, very little rotational force is needed to change its angular velocity because all its mass is close to the center line of rotation. All of its mass has a itty bitty small rotational inertia. So it has a small, all its mass has an itty bitty small radius. So it has a small rotational inertia, which means doesn't take much to, because it's like mass, it's like rotational mass, doesn't take much to change its angular velocity. All right, but now take that baseball bat, hold it this way, and now do this. It takes a whole lot more energy, a whole lot more rotational force to have it change its angular velocity. And if you really want to get, and the reason why is because when you look down here at that rotational inertia, which dictates how much it wants to, or its ability to resist changes in its rotation, okay, a lot of its mass is far away, big radius, far away from the center line. And remember, that part of it is squared. So that ends up being a big number, okay? And if you really want to get crazy, take a baseball bat, hold it at the end, and try and make it do this, all right? Or this, however you want to do it. That takes a tremendous amount of rotational force, okay? It's not easy to do. All right, so this is the rotational energy of I'm sorry, this is the kinetic energy of rotation. And the reason it was brought up primarily is to introduce you to this idea of rotational inertia, which is the equivalent to a rotational mass. Yeah, that's it. It's equivalent. It's the rotational equivalent to mass. All right, I got it now. I'm out of practice with doing these. Okay, that's it for now. Adios, everybody.